This is Bridget Walters presenting my final project in EE304. I did my project on Conway's Game of Life in MATLAB. What is Conway's Game of Life? The Game of Life consists of a two-dimensional grid of cells. Each cell is established as alive or dead and interacts with its 8 neighboring cells to determine whether it will still be alive in the following cycle or generation. To determine which cells are alive or dead is dictated by a simple set of rules. Any live cell with 2 or 3 neighbors survives to the next cycle. Any dead cell with exactly 3 live neighbors becomes a living cell, and any cells that do not meet rule 1 or 2 will be dead in the next generation. The reason this is called the Game of Life is because it simulates population. If a cell has fewer than 2 neighbors, it is said to be underpopulated and cannot survive. If a live cell has 4 or more neighbors, it is overpopulated and cannot sustain itself. Having 3 cells bundled together simulates an ideal population. At the start of this project, I put together an outline to summarize my project. This is a good practice for any coding project. My outline looked like this. Determining which cells are alive in the initial cycle, how big the grid system is and how many cycles it runs, statements to implement the rules of Conway's game, linking the cells to its neighbors, which determines the state of the cell, meaning alive or dead, and the output of the code would be a visual grid system conveying which cells are alive. Why did I choose MATLAB? I chose MATLAB because it is capable of outputting images, like the grid displaying live cells. I have used MATLAB before in a previous university and have a student license. Part of why I like MATLAB is because of its resources. It is not free like C++, and so because it generates revenue, there is funding for an organized compilation of MATLAB code. Having a license also gives you access to more information from MATLAB designers. So the code for my system was pretty short. I expected it to be longer, but this is all that I needed. So for my presentation, I thought I would just go through each component of the code since there isn't much to it. So just starting from the beginning, the x equals sparse 50-50, that creates a 50 by 50 grid. So that's going to be the size of my grid system. So if we go over to the requirements box, how big is the grid system? Check. Good to go. Okay. So the reason that I used sparse as opposed to other functions that build grids like mesh grid or things like that. So sparse only saves or only stores the values that are not 0. So given what this simulation does, it's just 1s and 0s. This is the perfect function for saving memory. So the next part of the code right here is, this is the statement that generates the random input of live cells. So the initial cycle, you have to have so many live cells, and then the system runs wild and just implements the rules. So the way that I chose to do this is this first part of the equation creates a 10 by 10 grid towards the center of the grid, and this matrix is then filled with this statement right here. So this says that you generate a random matrix that's 10 by 10. So this is going to input into the 10 by 10 matrix random numbers between 0 and 1. But that's not what I need. I need 1s and 0s. So how do I translate these random inputs to 1s or 0s? So that's what this greater than symbol does, is this statement as a whole is a true-false statement. So this saves any random inputs that are greater than 0.55. So if it is greater than 0.55, it gets saved in this matrix as a true statement, and a true statement equals 1, and a false statement equals 0. So that's exactly what we need for our grid system. So that's what initially starts the simulation, and then we move down to the for loop. So the for loop is going to run 100 times. That's how many cycles. Oh, and I'm getting behind on my requirements. So we just covered how many cycles does it run. So this requirement is good to go. That was supposed to be a check mark. And then to determine which cells are alive in the initial cycle, we covered that with this random input. So that's good to go. Okay, so we're going to run this 100 cycles. So that's going to be like 100 generations that we're going to do. So spy X, that just says, I want to see what X is doing. So X is going to be our grid system. So whenever somewhere in the grid equals 1, we want to see it. That's what spy does. So then this is just how to get a title on your grid. And so that will appear like at the top of your grid as if you were titling a graph. And so the num to string function that classifies T, which is defined up here. It just changes it from a numerical value to a characteristic or a character array, So it basically just transfers it to print so that we can display it. And draw now is a very common function in MATLAB, which, it does exactly what it says. It says draw now. So draw the graph. We want to see it. So initially, the first time that this code is ran, at this point in the code where it says draw now, we're going to see what the initial random input looks like. So we've got our initial random input, and then we start going through the rest of the code. So then this chunk down here, this is how we're going to implement all our rules. So if we scooch down to this next slide, this is the breakdown of communicating with our neighbors. So if this middle cell is ij, then the corresponding neighbors are going to be, this is I, this is the same row, but it's j minus 1. It's back one column. So that is interpreted into this equation. So in this equation, there are 8 components, and that is corresponding to each of the 8 cells. So then when we go back up to the code, looking at this part of the function, that's going to translate taking each value of x, and we're going to store it as a 1-by-1 grid as the value n. N gets put into an equation, into an array, putting out p and q values, where these p and q values are then going to translate into 1s or 0s. So it's going to define all of the neighbors of each x as alive or dead. So then that is going to get stored. We're going to summarize or get the summation of all of the neighbors. So if there were 6 live neighbors, y would equal 6. That's what we're doing. So then we come down to the next piece of code, and this is implementing the rules. It actually boils down to something very simple. So this statement is the same as this statement. So it's just got some extra spaces in here to let this line out. So what this piece of code, let me go back to the no colors. So this piece of code uses logic gates. We've got our AND symbol, we've got our OR symbol, and so logic gates operate off of Boolean algebra, where we're only dealing with 1s and 0s. So what this statement says is it reads, x is true if either, you got these two statements are broken down with the parentheses. X is true if either X is true and Y equals 2, or X is true if Y equals 3 is true. So those are the statements that we're breaking down. That's how you can have X and Y still turn out to be a 1 or a 0, is because we are asking for true statements in this expression. So then we end our for loop, and so it loops back around, starting off with the second cycle. It's going to show us now what X looks like after implementing these rules onto a new X. So it's going to show us our second cycle, and then we run through it again, and we do that 100 times. So since I'm screen recording, instead of doing screenshots of the code, I am just going to go ahead and run the code so that you can see how it looks over here. You can see up here at the top is what cycle we're on. And then down at the bottom, this NZ, this is counting how many X's equal 1. So how many live cells we have. And that is a property of the sparse function where it counts how many non-zeros we have. So you can see as the patterns run through, we do get stuck in certain formations. That's common of this. Otherwise, it just keeps changing, does whatever it needs to do. And then once we've completed our cycle, the code stops running. So that is my presentation on Conway's Game of Life.